This is a PowerPoint presentation on Chapter 14, 2WayANOVA. So we've already talked about 1WayANOVA, and we've become familiar with the concept of the mean square. So a mean square, as we've talked about before, is just pretty much the same thing as variance itself. That's just one way to look at variance. And as you see here from the equation, we can think of it as sum of squares over degrees of freedom. And we could think of it as the mean of the squared deviations from a mean. And in 1WayANOVA, we've seen that we can have between or within treatments mean squared values. And our F statistic has been a ratio of the two things. So we've had between mean squared over within mean squared is equal to our F ratio. Basically asking ourselves whether the variance from the treatments, the variance between MS, looks like it's extreme if you compare it to the variance within treatments that we see on the denominator of the F ratio equation. So again, you can see here F equals MS between over MS within. And as I said, a fraction looks at the numerator from the perspective of the denominator. That's a concept that we talked about a lot before. And so we're saying, what is the variance between the treatments from the perspective of the variance within a treatment? What you might expect if the null hypothesis is true.
So here's a way I like to visualize the sum of squares. So when you take a look at if we had two treatments, I think I went through this in a previous presentation just to recover how we're thinking about things. So if I have two different treatments, think about it as a red treatment and a blue treatment, all right? We can think about them each having their own within treatment sum of squares, which is represented here by the squared distances from the mean. So in the red, you see squared distances from the mean, and in the blue, you see squared distances from the mean, and that would be the within treatment sum of squares. Over here on the right, we see the total within treatments sum of squares, represented by the blue and the red squares around the same mean, as if they had the same mean, which is basically what we're pretending when the null hypothesis is true. Now, if I were to divide, if we remember what pooled variance does, if I were to divide all of those sum of squares by the sum of the degrees of freedom for each treatment, then I would be able to get some sort of pooled variance value. And in this case, we're thinking about it as the pooled variance within treatments. Now you see some new red and blue squares, and these red and blue squares are giving us a sense of the sum of squared distances of any one of the scores from the overall mean, as if you were to think of all of the squares as if they were in one big group. This is the total sum of squares, as you see that I've written at the top here. And again, you could just add all of these square distances together, and that would give you a value for the SS total. Now, when we moved on to 1WayANOVA, we added another treatment group. But everything works pretty much the same. You still have an SS total. This I'm representing just by three huge squares. There would be, those three squares would actually be made up of smaller squares for each value in the treatment, but you get the idea. You think about the SS total in the case of three treatments, you just make an analogy back to what I showed you for the true treatments, and notice that they all come from a general treatment mean. Now, what is SS between? SS between is when you take the means of each treatment and you figure out what is the squared distance from the mean of the means to any one of those specific means. Okay? The mean of the means here represented by this dashed gray line, which actually happens to be the same value as the mean of the middle treatment. And the squared distances from that mean are represented by these squares here. Now, the only difference between what I'm visualizing here and what the actual SS between looks like is that when you make a square to any one of these treatment means, you need to make one of them for every single score in the treatment. So think of it as having three red squares, right, for the three scores in the red treatment, and you would have 5 blue squares for the scores in the blue treatment, even though they're basically squares of size 0, and then you might have 3 green squares for the third treatment. And what we're doing in 2WayANOVA, sorry, I just jumped ahead for a slide there. What we're doing in both 1-way and 2WayANOVA is we're comparing between treatment values possible differences between treatment means with the differences you might see just within treatments. So in two-factor ANOVA, what we often do is we have 2 different parameters which we're varying. So this is an example from the textbook. You could have people who are given some type of exam or some type of thing to perform, and we're going to track the number of errors that they make in their performance. And you're going to have 2 factors at play here. One factor is going to be, are you going to put an audience of watching them or not? All right. In this case, it was cameras in the example in the textbook. So are these people being watched? Call that the audience treatment. Or are they not being watched? Call that the no audience treatment. And then we have another factor at play. Are these people already low self-esteem people, or do they happen to be high self-esteem people? So there's 2 factors. The 2 factors are whether or not there's an audience, and the other factor is level of self-esteem. And then we have what are called levels of the factor, and that's what's represented by the 2 different situations in each case. Right? The levels of the audience factor are no audience and audience, and the levels of the self-esteem factor are low self-esteem and high self-esteem. And what we see when we do two-factor ANOVA is we end up comparing the means of all these possible treatment groups, and there's 3 possibilities on what can happen. One possibility is that there's a difference due to factor A. We'll call that the factor A, the low and high self-esteem possibility. If there's a difference between those 2 levels of the factor, then you'll see in a plot like the one pictured below, on the left, you'll see a significant distance between these 2 lines, the line on the top and the line on the bottom, excuse me. If there's a significant difference between the levels of factor B, so what we're talking about here is no audience versus having an audience, then what you'll see is that the mean of the 2 values on the left, so think of that as the number right in the middle of these 2 numbers on the left, in the plot on the left, and the mean of the 2 values on the right are going to be different. There's going to be some sort of slope to the line drawn between the 2 means. Okay? So in this case, in this graph on the left, we actually see that there's a significant effect due to self-esteem level as well as whether or not there's an audience. I use the word significant liberally here because we haven't done a statistical test, but you can see there's a difference. Now there's a third type of significant difference when we do two-factor ANOVA, and that is when there's an interaction. An interaction means that it may or may not be the case that either factor A or factor B has an influence, but you will, in the case of an interaction, see a difference in the case of the interaction between the 2 factors. And so I'll explain that in this case here in this graph. All right? So what we see is that if you have high self-esteem, it does not matter whether you are being watched or not. You have the same treatment means for your 2 different groups, right? You see that in the box, in the table at the top, and you see that in the plot on the bottom. There's no difference if you have high self-esteem. However, if you have low self-esteem, it matters whether you're being watched or not. Okay, and you can even hear it in the way that I'm saying this. There's an interaction between the 2 factors, meaning you could say something like, it doesn't matter whether somebody's watching you or not, as long as you have high self-esteem. So you'll notice that I mentioned 2 factors there, and I have to qualify what's going on. So we can talk about this later, but just to give you a general sense of what we're looking at in two-factor ANOVA, we're looking at a significant effect of factor A or factor B or an interaction, and give you a general idea of how those things work. MS between is going to have 2 values when we talk about two-factor ANOVA, it's going to be the sum of squares for A over the degrees of freedom for A, plus the sum of squares for B over the degrees of freedom for B, plus the sum of squares for A times B, which is the interaction, over the degrees of freedom for A times B, which is for the interaction. We'll talk a little bit more about how you obtain those SS and DF values. So the error term in this case of two-factor ANOVA is the same as in the case of one-factor ANOVA. In the case of two-factor ANOVA, we just are adding generally at least one more group. A lot of times in what we see in one-factor ANOVA is we have maybe 3 groups. In two-factor ANOVA, we usually have at least 4 distinct treatments. And so what we can do is find, again, what I might talk about as a pooled variance value in order to find the MS within treatments. Basically what's going on, I'll go back a slide or 2 and continue talking about that within treatments number. So what we end up doing to find within treatments mean squared and also the sum of squared and so forth is we look at just within treatments values. So the within treatments mean squared would be adding all of the sum of squared values within each treatment and dividing by the degrees of freedom values within each treatment. And those are fairly simple. So for example, if we had 5 in each treatment, our degrees of freedom value would be 4 for each treatment, and our sum of squares value we would obtain within each treatment.
Okay, so now we have a basic conceptual understanding of two-way ANOVA, and I'd like to walk you through the mathematical steps necessary to perform a two-way ANOVA analysis. So I'm going to walk you through demonstration 14.1 from the textbook, try to give you some details as we walk through. So here it says the following data are representative of the results obtained in a research study examining the relationship between eating behavior and body weight. 2 factors in this study were the participant's body weight or the participant's state of hunger, either full stomach or empty stomach. And body weight is characterized as normal or obese, by the way. I'm going to skip over this SPSS data and continue. All participants were led to believe that they were taking part in a taste test for several types of crackers, and they were allowed to eat as many crackers as they wanted. Dependent variable was the number of crackers eaten by each participant. There were 2 specific predictions for this study. First, it was predicted that normal participants' eating behavior would be determined by their state of hunger. That is, people with empty stomachs would eat more, and people with full stomachs would eat less. Second, it was predicted that eating behavior for obese participants would not be related to their state of hunger. Specifically, it was predicted that obese participants would eat the same amount whether their stomachs were full or empty. Note that the researchers are predicting an interaction. This means the effect of hunger will be different for the normal participants and the obese participants. Data are as follows. Okay, so here we see data. It's similar to what we were looking at with one-way ANOVA. We're given small n's. These are the treatment sizes for each of our different samples. Notice that this sample is people who are normal, they're not obese, and they have an empty stomach. But you also have normal people who have a full stomach. You have obese people who have an empty stomach, and you have obese people who have a full stomach. Now, the prediction that the researchers originally made was that people are going to generally eat more crackers if they have an empty stomach. However, the obese participants in the study are just going to eat a ton of crackers, basically what they're saying. So let's take a look at the data here. The mean of the normal group for empty stomach is 22. For the normal group with a full stomach, the mean is 15. And so already we're seeing maybe a hint that the hypotheses are true, right? The mean is higher, meaning they eat more crackers when they had an empty stomach. Now let's look at the obese participants. The obese participants, the mean is 17 for empty stomach and 18 for full stomach. Again, this may be exactly along the lines of what the researchers are predicting, that there's not really much of a difference between the obese people, whether they have a full stomach or empty stomach. Over here, we have T-normal. Now, you have to think about this as, in a way, as though it was kind of like a t-test, like an independent measures t-test of just normal versus obese individuals, regardless of whether they had an empty or full stomach. And in that case, you'd be looking at a treatment total for the normal group of 740, and this is just, notice the sum of the total in each of the groups, and a treatment total of 700 for the obese set of individuals. And this actually, this T over here should say T obese. T obese equals 700. And also in the columns, we can do something similar. We can just look at empty stomach people versus full stomach people and try to see if we think there's a significant difference between those things. So here in an empty stomach, we see a treatment total that's 440 plus 340 equals 780. And then 300 plus 360 equals 660. So that's where these numbers come from. Now over here on the right, we still have the G number which we're used to, which is the grand total of all of the scores, which should equal to T1 plus T2 plus T3 plus T4. You just add all the treatment totals together. N80 is a total sample size, so that should be the number of each sample times the number of samples. So 20 in each sample times 4 samples, that would give us an N equals 80. And the sum of x squared, now that's going to give us, if we were to take each square, score it, and then add all those squared values together, we would get this number 31,836. And since we don't have the treatment data, each score individually, we would not necessarily be able to calculate that value on our own, so that's good that they're giving it to us. And then this overview of the values that are given to us. Of course, you understand what sum of squares are. So we won't go into detail on the sum of squares value for each treatment. So step 1, when we're doing 2WayANOVA, is to state the hypotheses and select the alpha level. Now we have multiple hypotheses. We have 3 null hypotheses here, I want you to notice. One is just for the normal versus obese people, that the mean of the normal and the mean of the obese people are going to be the same. We also have a null hypothesis for the full versus empty stomach groups. That's basically if we're just looking at the columns in this table. Okay, so again, the mean, population mean for full and empty should be equal. And then the third null hypothesis is that the effect of factor A does not depend on the levels of factor B, and then in parentheses, and B does not depend on the levels of factor A. Okay? And that's basically saying, well, there's no interaction. In short, that's what that null hypothesis would be. Now, if we want to come up with alternative hypotheses, we can again say in the case of factor A, we could say we're expecting the treatments to not be equal. Treatment means to not be equal. Case of factor B, expecting the treatment means to not be equal. And then, of course, the alternative hypothesis, the third alternative hypothesis would be that there is an interaction, or you could say the effect of factor A does depend on the levels of factor B, or vice versa. Okay? We set our alpha level. Now, that's all step 1. Step 2 is going to have a few stages because we have a little bit more complex calculations going on. So let's read what it says here. Rather than compute DF values and look up critical values, at this time we proceed directly to ANOVA. Sounds fair enough. Now, when you do end up looking up the DF values, you're still going to use the same process of using a degrees of freedom between and a degrees of freedom within. It's just that you're going to have to look up 3 different critical values based on your 3 null hypotheses, and we'll see exactly how that happens later. If not in this lecture, then in the one where I'm lecturing you in person next time. The first stage of the analysis is identical to independent measures of ANOVA, presented in Chapter 12, where each cell in data metrics is considered a separate treatment condition. So, if we want to find SS total, we can just use this computational formula, given the values that we have, that's found this way. Within treatment sum of squares, just as I was mentioning before, we can take the sum of squares within each treatment, which is listed in that table, and add those together. And this is, again, this is a step kind of like we would take when we're calculating pooled variance. And finally, if we want to calculate the sum of squares between treatments, we use this equation, the sum of t squared over n minus g squared over n. Very similar to the equation from the last unit. Notice, similarly, we have to find a t squared over n for each sample. T squared over n1, t1 squared over n2, t3 squared over n3, and t4 squared over n4, minus this value that we already have, g squared over large N, and we get a value for that. Now, the difference with two-way ANOVA is that between treatments, sum of squares values actually gets broken down even further. But first, let's talk about the degrees of freedom values. For df total, it's always the large N minus 1, so in this case 79. The df within treatments, you're subtracting 1 from each treatment number and adding them together. So instead of 20 plus 20 plus 20 plus 20, you have 19 plus 19 times plus 19 plus 19, or 19 times 4 equals 76. You can also think about this as big N minus K, right? That's big N being 80 minus K, the number of treatments is 4, and that would give you the same value. And finally, between treatments is the number of treatments minus 1. So in this case, we had 4 different treatments, various combinations of factor A and factor B, and we just subtract 1, and we would get a between treatments degrees of freedom of 3. Now, on to the second stage of the analysis. Now we have to partition between treatments variability into 3 components. The main effect for factor A, basically these are the 3 null hypotheses, if you noticed before. The main effect for factor B, and the interaction. So for factor A, we're looking at normal versus obese. So what we need to do is we need to find the sum of squares for A. And now what that's doing is we're looking at the sum of t squared rows over n rows minus this value we already have, which is g squared over n. So let's look at how that manifests itself. So 740 squared over 40 plus 700 squared over 40. N is the n of a row. If you notice, there was 20 in each cell, so if there's 2 cells in a row, then you're going to add those n's together and you're going to get 40. Now let's look where these numbers 740 and 700 come from. What we're getting those numbers from are the treatment totals for the rows. For row 1, 740. For row 2, 700. So here's how you get the sum of squares for factor A, or the factor where you're talking about the difference between the rows. And this is just a simple matter of using these numbers once you know where they came from. Factor B is going to be very similar, except we're going to do things looking at the columns. T squared columns over n columns. And you can deduce how to do that based on how we just did the rows. And finally, we need to find the SS for the interaction. And we basically only calculate the SS in the interaction when we already have the sum of squares for A and the sum of squares for B. And we do that by subtracting those 2 values from the sum of squares between treatments value, which we also need to already have. And the details of the calculation in this particular case are right here. Finally, we need to find the corresponding degrees of freedom. The degrees of freedom for A is the number of rows minus 1. The degrees of freedom for B is the number of columns minus 1. And then finally, the degrees of freedom between treatments is the degrees of freedom of the interaction, notated here as A times B, is the degrees of freedom between treatments minus the degrees of freedom A minus the degrees of freedom B. Well, in other words, 3 minus 1 equals 1. And then finally, we need to calculate MS ratios for each of those null hypotheses, right? For A, we need to take the sum of squares of the degrees of freedom. For B, sum of squares over the degrees of freedom. And for the interaction, sum of squares over the degrees of freedom. Now we have 3 MS values, and we also have a within treatments MS value, and that is, again, the sum of squares within treatments over the degrees of freedom within treatments at 71. And now we can finally calculate 3 F ratios. Based on the numbers that we already have, in this case, we have a 20 over 71, MSA over MS within treatments, 180 over 71, MSB over MS within treatments, and then finally 320 over 71, which is MS interaction over MS within treatments. Notice MS within treatments is on the denominator of all free fractions. Why? That's what's known as the error term. This is the level of variability expected if the null hypothesis is true. What's the null hypothesis? If each one of those separate samples is all actually from the same population, that there's no difference between the population means in the null hypothesis case. So that's where why this MS within treatment is seen on the denominator of all three fractions. And that's something you should notice and remember if you're tested on that particular fact. So finally, once we get the F ratios, we can look up the critical values. And now that you have your degrees of freedom for A, B, and interaction, now you can look up your critical F values in the table. So you would use your between treatments and within treatments values for each one of those situations. It just so happens that your between treatments degrees of freedom is 1 in all three cases, but sometimes it's not always 1 in all three cases. So you have a critical value that's the same for all three tests, and now you just need to compare the values that you got with your critical values. So your critical value is 2.98. The first value you got, 0.28, it's not big enough. So you have to fail to reject the null hypothesis. The second value you got, also not big enough. You also have to fail to reject the null hypothesis. And finally, the third value you got is larger than 3.98, and so you actually reject the null hypothesis. And as it says here, this means that the effect of fullness does depend on weight. A closer look at the original data shows that the degree of fullness did affect the normal participants, but it had no effect on the obese participants. And that's all I'm going to go through for this moment, but we can go through how to calculate a two-factor ANOVA problem a little bit more in class. I hope you found this helpful, and I will see you again soon.